All right, so we start. So thanks for coming. So today we are pleased to have Euiwoong Lee from University of Michigan. And we talk about parameterized approximation.
Thanks for the introduction. Thank you for inviting me. So this is a joint work with a lot of people. It's not just like one paper. It's a series of papers that I did for like past many years. Not many, like less than 10 years. And then yeah, you can see my collaborators here, especially Euiwoong Lee is here, and then her collaboration with me, I think, started here at IBS in 2019. And then more generally, I'm a computer scientist, so I'm like designing algorithms or like prove that certain algorithms don't exist. And then I bring here like math problems, and then sometimes you guys solve it. Okay, so let's hope that this happens again today. And then let me begin. Okay, so the outline, it's more like survey talk. Okay, so there will not be like huge like deep mathematics. Instead, I'm going to give you like some algorithmic ideas for some basic optimization problems. So yeah, I'm going to give you like some introduction or survey to the area, and then there will be like 3 classes of optimization problems that we're going to study. And then I'm going to, I mean, none of this direction is closed, so everything's open. And then among them, I'm going to show you my 6 favorite open problems. I think they're like each of them is like the computational problems, where they're like there are like better algorithms, or like you gotta prove that there is no better algorithm. So they are like computational problems, but there is like for 2 of them. Let me try to boil them down to like some crisp math problems, so that you can think about it on your own. Yeah. Okay. Again, and then again on the way, I'm gonna show you like some like basic algorithmic or complexity theory tools, like tools that theoretical computer scientists use. So again, like there should not be any like technical things, but then if you, I mean, but then like languages will be different. So if you have any questions, just like stop me. I don't have like many materials anyway. Okay, let's get started. Okay, so the one kind of huge theme that we are gonna study is this thing called the Vertex Set problems. Okay, so it can be very general. Let's say like F is some like nice family of graphs. Okay, so like it can be like family of all bipartite graphs, family of all planar graphs, like family of all your like favorite graphs. So if you fix like this family F, then one can think about like one optimization problem called the F Vertex Deletion problem. Okay, so here like it's a parameterized by S, so like one F gives you the one problem, and then in this optimization problem, the input is a graph G, and then all you want to do is to make sure that the graph belongs to F, your favorite class, by deleting the vertices. Okay, so you want to output the smallest set S, such that if you delete the vertices S from your graph, then this resulting graph becomes the member of a family F. Okay, and then I want to minimize the number of vertices you delete. Okay, so yeah, any questions about this framework? And then of course, if you can try every like subset, then it's gonna be easy. Like it's gonna be exponential time. So we are interested in polynomial time algorithms to get the best approximation for this objective function.
So do we require F to be closed under taking induced graphs?
I think yeah. All I think it's gonna be all our families will be like closed under something, at least like in the old examples. Okay, it's gonna be the minor or like subgraph or induced subgraph, depending on the context. Okay, so here are like some interesting families that people have studied separately. Okay, so probably like the most simple class is like the graph with no edges. Okay, so this is called vertex cover. Basically, you are trying to delete all the edges by deleting vertices. Okay, there's a 2 easy 2 approximation algorithm, and there's amazingly actually that this 2 approximation is known to be tight if you assume some complexity conjecture called unique image conjecture. And then another interesting class is like the Treewidth Vertex Set. Okay, so it kind of behaves differently whether you look at the directed graph or undirected graphs. But then again, amazingly, in undirected graphs, there's like 2 approximation algorithm. Again, it's tight. And then if your F is a bipartite graph, then it's known as all-cycle transversal. And then there is square root over log n approximation algorithm where n is the number of vertices. And then again, that is kind of like shown to be tight. There's no constant vector, and so on and so forth. Okay, so there are like some open problems, but then this is some class of problems that people have studied so far.
When you say hardness, are they all depending on the same kind of assumption, or are they different assumptions?
I think these guys, they all rely on the unique image conjecture.
So what does this omega 1 mean?
there's no constant approximation. Because like yeah, unique games conjecture, I think they're not gonna give you like some dependence on n, only or only on constant factors. Cool. But then yeah, there are only like 5 examples, and then one can create like there are like infinitely many families of graphs. Okay, so you want to be like more systematic in terms of studying these graphs. And then yeah, people were thinking about then yeah, what is a systematic way to consider these the family of graphs? And then one way to do it, I think as someone mentioned, is the H something deletion problem. Okay, let's say that Smiley, this guy, is like some notion of subgraph. Okay, so it can be like just usual notion of subgraph or like induced subgraph or minor. I think we're going to focus on these 3 things. Okay, so Smiley is one of them. And then H is like, it can be just like one fixed graph, or it can be like family of finitely many graph. Okay, so H will be the list of formative graphs. We want our graph to not have H as one of these the notions. Okay, so then once you define H and then once you define Smiley, then I'm going to define my family F as all the graphs, excluding H as a Smiley. Okay, so then I can easily capture all these problems. I think vertex cover, I can simply let H to be like single edge, and then Smiley to be a subgraph. Or if I want to say P-J vertex set, so then I can choose like H like just like one simple triangle, and then I want to exclude triangle as a minor. Okay, then the F will be like sort of all like forest. Okay, so does that make sense? Okay, so then and then it kind of captures like more like numerically parameterized problems. I think some problems we're going to look at is called the Treewidth Deletion. Okay, so here the graph is the input is a graph and then one parameter k, and then again your goal is to delete the minimum number of vertices to ensure that the treewidth becomes at most k. Okay, so that's a Treewidth Deletion, and then k path transversal is just like trying to make sure that your graph doesn't have a simple path of a length k. These are all like natural optimization problems. And then there are like many things that I will not talk about in this talk. I think yeah, we'll be talking about vertex deletion. I think edge deletion is another interesting research direction. And then parameterization by opt. Okay, so not what I'm going to talk about. I think this is also something that was studied a lot. But then I'm going to not mention this. And then yeah, whenever you want to like minimize the number of deleted vertices, you can always think about the reverse objective function, which is like maximizing the number of the remaining guys. Okay, because like yeah, these in terms of exact optimization, they're like exactly the same thing. But then in terms of approximation, actually they can be quite differently. And then actually, in this guy, I think actually is already proven like 30 years ago to be really, really hard to approximate. Okay, so basically they are like as hard to approximate as an independent set. So if n is a number of vertices, then even like n to the 0.99 approximation cannot exist. Okay, so max version is really hard. Actually, like by the way, is everyone fine with the alpha approximation algorithm? Yeah, are you guys familiar with this notion?
Maybe not. Some people said.
Okay. yeah. Good. So yeah, let me just like explain in words. Okay, so yeah, we are always talking about some optimization problem, and then our goal is to minimize objective function or like maximize objective function. When I say alpha approximation, so alpha approximation algorithm is a polynomial time algorithm that's going to find you some solution whose value is within alpha factor of the optimal value. Okay, so for vertex cover, if I give you like if I say like 2 approximation, then it's going to give you like some vertex cover whose size is guaranteed to be at most 2 times the optimal value. Okay, so that's okay. So then let's dive into like some problems. Okay, so first one, probably the easiest, simplest one is when Smiley is just like regular notion subgraph. Or one can it's also the case that we only have like one graph in the family. Okay, good. Okay, so then yeah, we have this problem. Suppose that H is like one graph with k vertices. Okay, so the parameter regime is that k is like some constant. Okay, so if you care about polynomial time, then n to the k is a valid running time, or like n to the any function k is a valid polynomial time. Then if you give me this H, suppose that this is a large graph and then H is a triangle, and then I want to look at this problem called the H-subgraph deletion, or like H transversal, which is just what we discussed. I want to remove the minimum number of vertices from G, such that G doesn't have an H as a subgraph. Okay, so in this example, how many vertices do I need to delete in order to destroy all the triangles? Two? Two, yeah, I think I had two. Two. Oh, which two?
Top two, maybe?
Top two? Then top two, I think the any these two?
Right.
Yeah, then remaining is a tree, right?
Oh,
That's-
I think you're right. Okay. Yeah, so that's all. Yeah, optimal value is 2. This is the solution I found, which is a 1.5 approximation.
Yeah.
So yeah, so this is a problem. And then whenever H is a k vertices, then I'm gonna claim that there's a very simple k approximation. Okay, so the way you do it is you just you find any type of triangle here, and then when you find the triangle, delete all the vertices of the triangle. Okay, so then whenever you find the triangle, you delete 3 vertices, and you just repeat. Okay, more generally, if you have a copy of H, okay, which has k vertices, delete all the k vertices and repeat. Okay, so by doing that, if you found say like L copies, then you delete k times L vertices. At the same time, you also find the L disjoint copies of H. Okay, so that certifies that your solution is a k approximation. Okay, so I think this was kind of fast. Any question about the k approximation thing? Yeah, it's kind of like the packing covering duality type of thing. Okay, so anyway, whenever H has a k vertices, this is k approximation, or we can interpret this as the matching in the k uniform hypergraph. Okay, so for any matching in k uniform hypergraph, there's an easy k approximation. Okay, so then k approximation is fine, but then can you do better? And then the first result I did in this space is actually -1. We proved that if H is a 2-vertex connected graph, then this a stupid k approximation algorithm is actually optimal. So if H is a 2-vertex connected, and then if you assume some complexity conjecture called unique games conjecture, then you cannot even get k minus 0.1 approximation. Okay, it's the stupid k approximation is exactly tight. It's kind of interesting when H is kind of this cycles over length k and k is constant, then actually then this problem, I think k approximation is still tight. Whereas I already told you that if you want to hit all the cycles, then there's a 2 approximation. Okay, so somehow hitting only short cycles is a harder problem computationally than hitting all cycles. Okay, so anyway, but then 2 connected is hard. Okay, I'm done with that. But then so then it remains to study 1 connected graphs. Okay, and then perhaps 1 connected graphs, I might be tempted to study trees. And then for me, if I say a tree, then perhaps there are 2 extremes. Okay, there might be more extremes, but then it's 2 extremes.
So when you say 1 connected, you mean
not
2 connected, right?
Yeah. Exactly. But then, it's gonna be boring if you have a cycle and then 1 cut vertex. Yeah.
Okay.
Okay, so there are 2 extreme cases that I have is the k star. It's 1 vertex connected to k minus 1 leaves, or just simple k path. Okay, so for me, these 2 are the 2 extremes of the trees, extremely low diameter, extremely high diameter. And then I thought about this case, and then if you think about it, then if you look at the k star transversal, and then suppose that your input graph G is a k minus 1 regular graph. Okay, so if you look at if your G is a k minus 1 regular graph, then the only copies of k star is just 1 vertex connected to k minus 1 neighbors. And then if you want to hit all these the k stars, then all you gotta do is for each vertex you want to hit the vertex itself or one of its neighbors. Basically, you want to reduce the degree from k minus 1 to k minus 2, max degree. If that is true, then you're hitting all the k stars. And then probably I think this problem has a name, dominating set. Okay, so for every vertex you gotta hit the vertex itself or one of its neighbors. So it's at least when G is k minus regular, this problem exactly becomes a dominating set. And then the I'm going to say this is some problem that computer scientists like thought about a lot. Okay? In this case, log K approximation exists, and then it's shown to be tight. You can't do better than like log K approximation. Okay, but then still like log K is a lot better than K approximation, so I'm going to consider that as a success. Good. And then K path. Okay, so and then we prove that even for K path, log K approximation exists. Okay, so yeah, I might say a few more words about it, but then this is a problem that kind of introduced me to this notion of Treewidth, because like the argument goes like if G doesn't have a K path, so then yeah, one can easily see that G has a bounded Treewidth. And then we use this Treewidth property to design some algorithms. If I have more time, I'm gonna say a few more things about it. But then at least I told you that okay. Whenever I see tree, like I see like two extremes, but then both of them have like log K approximation algorithms. Okay, so they are like very different algorithms, but then like at least like both of them like are log K, much better than K. Okay, so then it's okay. So I've two extremes are log K. So okay, so my conjecture was every tree should admit like log K approximation. Okay, so that's my secret conjecture. I don't think I gave it formally as a conjecture at some talk. Otherwise, it would have been embarrassing.
That is hitting as subgraph.
Yeah. And then 21 actually like these guys at least gave some evidence. Okay, so they show that whenever H is a tree, then they can shape from this like trivial K approximation. Okay, so these guys got K minus half approximation. Okay, so which is pretty exciting for me. At least the trees behave better than every tree is being better than just cycles. So I started my faculty job, and then there was like one undergrad, and then I just like gave this problem. Okay, so like this is the problem. Like just prove that every tree has like log K approximation. And then he got the problem. He came back, and then he started to work on this like the special case called double tree. Okay, basically just like two center vertices connected to the K minus K over 2 leaves each. Okay, so I didn't understand why he was looking at this case. But then the worst thing is that he couldn't even make a progress. I kind of wanted him to design a log K approximation, but then he couldn't. And then he seemed to have some reason for that. And then I was like, why couldn't you do it? And then I went back to it, and then we were discussing, and then we realized actually this is actually the hard case. Okay, so when the H is double star, actually we proved that forget about log K, even like K over 2 approximation, you cannot beat it. Okay, so that's very simple reduction, but then that's something I missed like for many years.
So the previous algorithm, was it like K over 2 minus? Can you?
There's like K minus half.
K minus half.
And then this hardness is a K over 2.
Oh, I see. So, okay, this makes sense. Okay. Yeah.
Okay, so so this is kind of very simple reduction that I missed. Let me at least tell you something about the reduction. Okay, so the hardness is from general hypergraph vertex cover. Okay, so the input is that, let's say like LHDC. Okay, so your input is like L uniform hypergraph H, and then you want to find the smallest vertex set S that intersects every hyperedge. Okay, that's a hypergraph vertex cover problem. And then for simplicity, let's assume that every edge has exactly L vertices, and then degree of each vertex is D. Then it's kind of like the set cover problem in computer science, or the heating set problem. Dominating set, they're all related, and then the fast approximation ratio is a minimum of L and log D. Okay, so depending on L and D, like one algorithm might be better than the other. But then at least when these are very large, actually one can prove that this the L approximation is tight. Okay, so there's not even like L minus a 0.1 approximation. And then we are reducing the hardness of that problem to our problem. But then before doing so, let me just like rephrase this like hypergraph vertex cover as like the graph problem. Okay, by just looking at this the easy vertex hyperedge incidence graph. Okay, so then if you look at this example, okay, so I listed all the vertices on the left side, I listed all the hyperedges on the right side. So then by my assumption, then the right degrees are all L's, and then left degrees are all D's. And then we are assuming that D is much larger than L, because in order for this hardness to kick in, then D must be larger than much larger than L. So then one can kind of really see that hypergraph vertex cover problem is to delete the minimum number of left vertices, because we are deleting vertices of the hypergraph, to reduce the right degree, which is all L's here, from L to L minus 1. Okay, so that's just like the reformulation of a hypergraph vertex cover problem in terms of the incidence graph, bipartite incidence graph. Then now you can see kind of similarity between this problem and then the problem we were discussing, just subgraph deletion, because like it was about the reducing the degree of a subgraph. Okay, so then so we look at this incidence graph, and then we look at this hardness result. Then basically one idea is, the idea is that if then now I think we kind of converted. We are trying to convert this hypergraph vertex cover problem to our double star deletion problem. And then we want to say that if S is a solution for hypergraph problem, then it is a solution for the graph problem as well, and vice versa. And then at least one direction is very easy to see, because if S is a solution for the hypergraph problem, okay, so then we know that deleting S will make the right degree at most L minus 1. And then once you make sure that all the right vertices have a degree at most L minus 1, then then it means that for any the two vertices connected by an edge, okay, so either like one of the vertices should have a degree L minus 1, because if it's a bipartite graph, so at least one guy should be on the right side, and then that guy should have a degree L minus 1. So if the K is 2 times L, so then there's no way that the resulting graph will contain a double star, the K double star. Okay, so if S is a solution for LHDC, then this is a solution for K double star deletion in this graph when K is 2L.
Can you draw? why we cannot have K double star?
Yes. So yes.
Ah, okay. L is smaller.
Yeah. So this so this guy is I think L. This is L. Okay, so if I delete the left vertices, so that every right degree is at most L minus 1, then how can you have this kind of structure as a subgraph? Because like whenever you give me whenever you want to find it, at least one guy should be a right vertex, and then that guy's degree is always well reduced to like L minus 1 at most. Okay, so there's no way that you're gonna have this guy as a subgraph. It's kind of it's a stupid reduction that I missed for like 5 years at least. Okay, so that proves the hardness of this case. Okay, so now the right answer is between K minus half and then K over 2. And the other directions are also easy as well. Okay, so then my first open problem is now just like, okay, I proved the K over 2 hardness. Okay, so then my new conditions every tree has a K over 2 approximation. Okay, so that's open problem. Even like 0.99K instead of like K minus half. I think it's gonna be interesting.
Are there any other optical construction than two vertices of high degree being adjacent? Maybe that's the only obstruction.
This one. Do you mean just for double star or?
I mean, if the tree does not contain a double star of certain size, then maybe
Yeah.
not conjecture like the tree.
Yeah. I think. So I mean, of course, I think there are really some like particular like very small examples, and then always but then those guys are not. When the algorithm can handle those guys. So I think always a game is you're right. I think coming up with some kind of very like tight obstructions, and then handle some like other like boundary cases separately. That's been the case for algorithms always. Yes. Good. Okay, so then let's move on to the second class of problems, which is induced subgraph. Okay, so now I think everything is the same except that smiley becomes an induced subgraph And then now I think in this class, I think H is going to be like not just one graph, it's going to be like a class of infinitely many graphs. Basically, actually many, but in this class, I think I only studied within perfect graphs, or like it's a special cases. Okay, so just to make sure we are on the same page, whole is a induced cycle length at least 4. And then perfect graphs are the graphs that doesn't contain any odd hole or it's a complement. And then choral graphs are the graphs who doesn't contain any hole. And then distance heritage graphs are the graphs that doesn't contain any hole of length at least 5. Gem, house, and domino, where like these graphs are just basically what they suggest. But then yeah, these guys are like some famous class of graphs that are defined by the forbidden induced subgraphs. And then again, our question is, okay, suppose that we are looking at the choral graphs, and can you delete the minimum number of vertices to make sure that your graph becomes choral? Okay, and then here, big open problem is getting constant factor for like either choral graphs or distance hereditary graphs. Okay, so already like for the general perfect graphs, I think already like at least constant approximations rolled out. And then for choral graphs or distance hereditary graphs, I think polylog approximation is known, but then constant approximation, I don't know whether it can be achieved or not. And then what I did with Chung-Ho and In-Jung when I visited IDS was to design constant approximation for the class called the Ptolemite graphs, which are exactly the intersection of choral graphs and distance hereditary graphs. Okay, so I found this collaboration like very interesting because I'm doing approximation. So I brought half the tools, okay, basically the linear program rounding, and then Jung and Un-Jung like brought their expertise on graph theory, mainly how to characterize Ptolemite graphs in terms of this like weird fascinating auxiliary graph called intercalated graph. Okay, so I'm not gonna say more, but then this is like kind of a nice example where like tools from both areas were like gelled together and then get something. Okay, so that was like the second class. We have like 4 more. But then I think it's probably, if you're in this space, probably minor might be the most interesting topic to study. Okay, so now let's say that H smiley is a minor, and then I want to exclude H as a minor. Okay, so then of course, I gotta define what treewidth is. How many people do not know what treewidth is? I think I'm talking mathematicians, so I think no one, right?
Well,
okay, so tree decomposition is like the tree whose nodes are subsets of vertices that are called backs, such that unit of backs are the entire vertex set. And then if you look at any original vertex B, then the backs containing B induce a connected subtree in the tree decomposition. And then for every original edge, there is a back containing both U and B. Okay, so it's a standard tree definition. And then treewidth of G is a minimum over all decompositions, the maximum back size minus 1. So that's treewidth, central object in structural graph theory. Then one can look at the treewidth K deletion. Okay, again, the input is a graph G and integer K. You want to delete the minimum of vertices to make sure that treewidth becomes at most K. Okay, so then this problem, I think we designed a log K approximation already for a problem. Okay, so and then the running time is like some exponential function of K times n to the constant, if you care about it. And then we know that we cannot do anything in poly of nk time because like it's NPR to decide whether even there is a simple path of length k or not. If you want your running time to be like polynomial in k as well. Okay, so running time is kind of optimal, and then it improves the previous results. And then so that was for like this the Treewidth Deletion problem. But then once you have this, so then I can deal with the H minus deletion problem with any graph H, which is a planar graph, because I can use this heavy theorem saying that if your graph G is H-free, doesn't have H as a minor, and then if H is a planar graph, then one can show that your graph is bounded by a polynomial in H. Okay, so then using this algorithm for treewidth K deletion, then by only paying log K approximation factor, then you can reduce the tree to some parameter, and then you can do dynamic programming to roll out H. Okay, so overall it's gonna give you like log K approximation. And then one way to our way to solve this problem is somehow like again it's the same story. Somehow like gel the tools from approximation algorithm and structural graph theory. Okay, so from the approximation algorithm we solve this auxiliary problem called the K subset vertex separator. Okay, so again the input is the graph G and then some subset R vertices. Let's call them red vertices, and parameter K. And then I want to remove the minimum vertices such that after deletion, each connected component has strictly less than K red vertices. It's a reasonable problem. And then let's look at this example again. And then I claim you can delete red vertices. You can, it's gonna count 1. And then I claim that this problem, I think optimal value must be 2. Any objections?
Oh, yes.
I think it's 2. However you slice it. Or you can just like delete 2 red vertices. I think that's valid solution. Okay, so and then for that problem, we designed log K approximation algorithm, and then it's kind of using the standard tools from approximation algorithm. Actually, sorry, I think, but then that's the half of the algorithm. And then the cooler part, which is like graph theory part, actually I forgot to say it here, is that once you get the alpha K approximation, let me slide here. So once you get the alpha K approximation for this the benign looking graph partitioning algorithm, KSBS. Okay, so then it automatically implies the order alpha plus probably K plus 1 approx for K Treewidth Deletion. Okay, so that's that's interesting. That's cooler thing. Okay, so once you give me like this approximation, any approximation for this problem, I can automatically use this to get almost the same approximation ratio for like Treewidth Deletion problem. Okay, so if time permits, I might talk about it, but then I don't think I will. But then this is something I talked at IBS like 5 years ago. I don't know whether the video is still there or not. Okay, so that's some problem. Okay, so then in terms of improving approximation ratio for this guy, then all I gotta do is to improve the approximation ratio for this guy, right? Okay, so then that's what I wanted to do. I mean, log K is pretty good, but then I want to see whether there's this dependence on K is inherent or not. Okay, so it might be the case that actually this problem again it's 2 approximation algorithms for every K. Okay, so that's I think still open problem. Is there absolute constant approximation algorithm for this problem? Okay, so then in order to do this, then constant approximation for KSBS is suffices. And then even when everybody is a red vertex. Okay, so then the problem much simpler, everything is red, and we are just interested in the size of each connected component, bounded by the most K. Okay, so even that guy, I don't know how to do it. I don't know how to do better than log K approximation. And then this is a part I'm gonna spend some time from now. And then one can also think about the edge version. Okay, so it's called we adopted as the K edge separator. Okay, so you're just given a graph and then you have a number K. I want you to delete the minimum number of edges now, so that each connected component has at most K vertices. Each connected component has at most K vertices. Okay, so that's so somehow the edge version is slightly easier than vertex version. So it admits 2 approximation, and then it's a very interesting problem by itself to see whether this guy has 2 approximations height, or can you get 1.99 approximation. Okay, so then let me spend some time on these problems, but then let me explain something for the edge version first, and then go back to the vertex version. Okay, so then again this the K edge separator, as I told you, input is a graph G and K, and then I want to partition the vertex set into V1 through Vt. The only requirement is that each part has at most K vertices. And then I want to minimize the number of edges crossing is the T parts. Okay, so the only requirement is that every part has like most k vertices. And then again, you can think of the k as some constant. So n to the k is a valid running time. Okay, so then and then I'm going to show you how to get to approximation for this problem. Let's try to do it. Then if it's it's a very typical in approximation algorithm literature. Okay, so once you have some optimization problem, then you relax into a linear program. You solve it and then you somehow round it back to the integral solution. Okay, so then let me try to do this. Okay, so then I'm going to set up the linear program of relaxation for this problem. Okay, so then my variables will be this like z sub s for every subset of vertices that have at most k vertices. Okay, so the number of variables will be like n to the k roughly, which is fine because I n to the k running time I can deal with it. And then my ideal meaning is that zs should be like either 0 or 1. And then I want zs to be 1 if and only if that set s becomes one of my parts. If that is true, then I want zs to be 1, otherwise I want zs to be 0. That's my ideal intention. Okay, so then at least the objective function, you can write it like this. Because, so of course, like if z is 0, then I don't care. If zs is 1, if the s becomes one cluster, one part. So then basically, then it certifies that I'm cutting all the edges, crossing s. And then all edges double counted. Okay, so I got to divide it by 2. So this is objective function. And then the constraints are extremely easy. Okay, so the only constraint I'm putting is that every vertex v should belong to exactly one part. Okay, so if you sum over all the sets containing v, then their summation of z's value should be exactly 1. And then this should be like between 0. Okay, so that's the LP relaxation for this problem. And then it has n constraints, n to the k variables, so you can just solve it in point of time when k is a constant. Any questions about this LP relaxation? Okay, so then now of course LP can be solved in point of time. So we are assuming that we solve this LP to get the optimal z. Then now it's our job to round it back to the solution for my problem. And then actually this rounding algorithm is extremely simple. Okay, so what I'm going to do is that now I have LP solution, which basically gives like some number between 0 and 1 to every set s. Okay, so then what I'm going to do is just like it's an iterative algorithm. I'm going to sample like one set in each iteration. And then the way I sample is just like the randomly sampling as proportional to the zs value. And then I'm not going to even resolve the LP. So just like we use the same probability over and over again. And then of course like the only caveat is that so you sample this set. So this was a whole graph, and then suppose that this was your like the first set. Okay, so then you make this as like the first part. And then if the second sample is like this, so then what is the second set? Okay, so we just like do the obvious thing. So if this was the first set, then your second set is the secondly sample set, which is this guy, minus the part where is already taken out. Okay, so then this guy becomes a second set, and then we just proceed until like every vertex is covered. Okay, so it's very simple rounding algorithm. It's a randomized algorithm. And then it's also very easy to see that this guy gives you like 2 approximations. Because let's give one notation. Suppose that like when we have the 2 vertices u and v, let's say that x u v is kind of measure the distance between u and v. Okay, so ideally indicate whether like u v are separated or not. Because if u v are not separated, then it means that there is some cluster S that contains both u and v. So then the best summation should be 1, and then the distance between them should be 0. But then of course like if u and v belong to different clusters, then this summation must be 0, and then x u v must be 1. Okay, so x u v ideally indicates whether u v are separated or not, or at least one can define this linearly in terms of the z. And then here's one picture. If you look at u and v, so then there are these like 6 sets, S1 through S6 containing u. And then there are these 6 sets, S1 through S5 and S7 containing v. Okay, and then S1 through S5, they all contain u and v. So they are like fine. But then only the X6 and S7, they contain u and v separately. Okay, so in that case, then one can see that the value, the z value of S6 must be equal to z value S7, which is defined to be XUV. And then the summation of S1 to S5 should be like 1 minus SU. That's kind of a pictorial description of what's going on in this LP. So then, yeah, then one can look at this the objective function that we use for the LP, and then one can easily write this as a summation over UV with A XUV. Okay, because like XUV ideally must indicate whether UV are separated. Okay, but then okay, so that's good. Now let's try to analyze our rounding out. Okay, so I'm gonna look at edge UV, and then I'm gonna look at what's the probability that UV is separated by this kind of. I mean, it's very simple, but then it's iterative. It might be hard to analyze. But then the only kind of the stupid observation is that okay, of course it's an iterative algorithm. It's gonna like sample a lot of sets. But then unless the algorithm sampled one of these 7 guys, okay, suppose that you sample some other S8, S9, S10, but then they don't affect this edge UV at all. Okay, so they are none of them contains U or V. Okay, so as long as you sample like something out which is not in this picture, then the UV are still in the graph, and then we don't care about at least in terms of U and V. So then the only the set whose sampling determines the fate of UV is one of these 7 guys. Then the question is like among these like 7 guys, who's gonna be sampled first? If S1 is sampled first, then you know for sure that UV are not separated, because if S1 is sampled among these like 7 guys, then UV belong to S1 and they're removed from the graph forever. But then if you sample S6 or S7, then we know for sure that UV is separated. If S7 is first, then D goes with S7, and then be done. They're separated. And that's same as S6. Okay, so then that's it. So then the whole game is out of the 7 guys. Who is going to sample first? So and then UV will be separated if S6 or S7 is sampled first. Okay, so then if you look at all the events, okay, so there's like the sum of the probabilities will be 1 plus XUV, because the S7 that guy is double counted, and then among them the bad event happens with the S6 or S7. Okay, so bad event is S2 times XUV and then divided by 1 plus XUV. But then in the LP, in the linear program objective, we were already paying the XUV. Okay, so if you compare the probability that UV is separated versus how much UV was paying for the LP, just like that's just 2 problems. Okay, so that's a very easy analysis showing that this LP is that you can construct the integral solution whose expected value is at most 2 times the LP objective. Any questions? Then let's move on to finally the math open question. So then we know that the integrality of the gap of the LP is at most 2. Okay, so if you give me some feasible LP solution Z, then I can use that to construct solution, integral solution, whose value is at most 2 times the LP. But then always the question is is a 2 optimal value? Is like 1.9 possible? Or like the integrability gap is an example where there's significant gap between the LP value and then the integral value, optimal integral value, and then I'm trying to construct instance in an LP solution that has a large integrability gap. Okay, so let me give you my attempt, which I haven't succeeded analyzing. Okay, so this is my instance. Okay, so this I think this is kind of the Johnson graph. Okay, so the N is just like the ground set, and then my set of vertices will be like exactly L sets of ground set. Okay, so there would be like exactly N choose L vertices. Then if I look at the vertices A and B, A is L set, B is L set. and then I'm gonna put edge between A and B if their intersection is the kind of maximum possible, L minus 1. Okay, so then at least I claim that the degree of this graph is gonna be L times N minus L. Okay, so you see why? Because if I'm this L set in the ground set, so then in order to go to like my neighbor, so then I gotta decide, I gotta remove one vertex from me, and then I gotta add like one vertex outside me. Okay, so it's like the L times N minus L. Okay, so that's the degree of this the Johnson graph. And then we are still looking at the K edge separator. Okay, so I gotta specify what K is, and then I'm gonna for the reason that will be evident in the next bullet, I'm gonna let K to be like N minus 1, choose L minus 1. Because I want to get some nice sets. But then what are these like the nice sets of vertices? Okay, so then these are exactly just like this thing with SIs. I'm gonna fix like one element in the ground set I, and then I'm gonna let the SI to be the set of vertices, to be the set of all L sets that contain that fixed element I. Okay, so basically, again, the picture is that I fix one element. Suppose that this is our element 1, and then my vertices are like all these like L sets that contain like so this first element. Okay, so that's my set SI. Okay, so that, and then I claim that then if you look at the size of boundary of SI, so then I claim that it's going to be like very small compared to the number of total edges of SI, because if I'm already in SI, if I'm one set in SI, then it means that I'm containing the element I. And then I want to go to a neighbor. If I want to go to the neighbor outside S, again this example, suppose that I'm looking at this. Suppose that I'm looking at this set A in S1, and then if I want to go to a neighbor outside S1, then I have to remove this guy, because like if I still contain this guy, then I'm gonna be still be in S1, and then I can choose the whatever I want to add. There are like N minus L possibilities. Okay, so then my number of neighbors outside this set S1 is going to be only N minus L. So there's a difference between L times N minus L and N minus L here. Okay, so in that sense, like this the SI is very like non-expanding set. Okay, so I think if you look at this like normalized expansion, only the one of L fraction of the edges instead of the SI are going outside the SI. Okay, so when L is a large constant or like large number, then this expansion gets well. Okay, so then we know that. Okay, so then SI, and then you can see like where the size K comes from. Okay, so K is exactly the size by SI. Okay, so then if you think about the LP solution, so then this is this SI is a kind of good set for the Euro problem, because like it is a set that has exactly K vertices and then boundary edge size is small. So then at least for the LP, I can construct a solution using this, because I can just let Z sub SI to be exactly 1 with L for each each I in N, each Bn. Okay, so if I do this, so then I claim that it's a feasible solution for the LP, because basically all I need to make sure is each vertex is covered exactly one time, fractionally, and then one set A has like exactly L elements. Okay, so if it's a 1, 1, 2 all the way to L. So then basically what I did is that I picked up S1 with fraction 1 over L, S2 with fraction 1 over L, so all the L sets are picked with fraction 1 over L. Okay, so I found a perfect fractional packing, only using this like the non-expanding sets SIs. Okay, so that's at least LP sense, I think it's a very good solution. Okay, good. So then I construct an instance, I construct a graph, I construct a K, and then I construct the LP solution. Okay, so I think probably one can prove that this LP is an optimal solution, but then it doesn't really matter. Okay, so then in order to prove that this gives you a high integrality gap, so then all you gotta do is to prove that if you are looking at the actual integral partition, okay, so the partition that has at most k versus each part. So then you have to cut much more edges than what this LP solution gives you. And then but then before going there, I think so this set SI is kind of it's of course it's kind of like very simple set, but then this is something that computer science called non-expanding small set. Okay, so it's just small. Because if the n is much larger than L, then the SI, the size of SI is like small compared to the total number of vertices. That's a small. And then we saw that expansion is at most 1 L. So it's a non-expanding small set. And then recently, I think in the recent 5 or 10 years, I think somehow characterizing small set expansion is a kind of the big field in computer science. For many decades. And then so far people kind of use the graph which are already like small set expanding, which means that all small sets expand. Okay, so we only use these kind of graphs. Okay, it's like hypercube is one of them, and then we always like use the graph where all small sets are expanding anyway. But then now I think to be more complicated, the trend is that now we are willing to look at a graph that has like some non-expanding small sets. Like this guy, as long as we can make sense of what they are. We can structurally characterize what they are. Okay, and then, so I think, this has been only a huge influence of computer science, especially hardness approximation, but in some other areas. And then, if you heard about this thing called 2-to-2 gain theorem, which is like half of the gains conjecture. I think these guys characterize this like the non-expanding small sets of I think the close cousin of a Johnson graph called the Grassman graph. Where like vertices are like subspaces, and then they on edge when they're displaced okay, good. So then back to our case. So we know that SI is this non-expanding small set, and then one can ask, okay, so what's gonna be the non-expanding small set in this graph like? So that question, I think, in some primary regimes, these guys already answered this question. Okay, so basically, at least in integral term, they say that all non-expanding small sets must look like this. Okay, so meaning that if you condition on the containment over like some small elements R, so then basically that should describe the whole set. Okay, so that's fine. I don't know whether I don't think that immediately implies what we want to do. But then our question, our question is just say that, okay, so in this graph, if you look at any valid integral solution, partition of Vertex Set such that each part has at most k. So then I want to show that, okay, so the number of edges you have to delete, to cut, should be at least like almost 2 times what you're going to get from LP value. And then it's kind of reasonable to expect. Because if you look at SI, then of course SI is like optimal expansion, but there's like no way that you can partition your like Vertex Set using SIs, because perhaps like in the first iteration you can fix the one element, and then you can take all the sets containing the first element, but then you just cannot iterate this procedure forever. Okay, so it's impossible to partition V with this like non-expanding small sets SIs. So I think that's I think these kind of proofs like use free analysis, but then I'm kind of open to I think there might be some simpler combinatorial proof for I think this conjecture, because I think maintaining a partition I think is just like a stronger thing than characterizing the small sets. So it's one kind of map problem. I think it's cute. I don't know. If you have any ideas, just let me know. And then okay, let me just spend 1 more minute. Okay, so then of course this was like the H-Deletion Problem, where where we were trying to figure out whether the 2 is tidy or not. Okay, so then actually one can if you want to go back to the vertex case, which we were discussed for the Treewidth Deletion anyway. Okay, so then instead of vertex deletion, I think let me just still give you hypergraph edge separator. Okay, so it's just like the same thing, but then the only thing that's changing is that now the graph becomes a hypergraph, and then you want to partition the same thing. Each part has endless k vertices, and then now I want to minimize the number of cut hyperedges, okay, which means that the hyperedge is cut if it intersects at least 2 parts. It's not contained in the 2 part. Okay, so yeah, I'm running out of time. So like just like LP, basically it's the same thing. It's like Z sub S for every subset S of a size endless k. And then one can write them down the same thing. The objection function is a slightly different, but then it's basically the same thing. And then here, like my conjectured instance is all kind of like a similar thing. Okay, so again, so now like B again it's n choose L. Vertices are the same, and then hyperedges correspond to L minus 1 sets. Okay, and then B, which is like L minus 1 set, will contain A in the hypergraph sense when the B is contained in A in this Brown set sense. So that's my hypergraph. That's my hypergraph. And then, yeah, sorry, yeah, it should be like K minus 1, N minus 1, choose L minus 1. The same thing. Okay, so then one can kind of do the same reasoning. So if I fix I and then let SI to the set of vertices that contain the fixed ground state element I. So then, yeah, then again one can see that the LP solution will be pretty good because yeah, if I look at one hyperedge, then if I look at one hyperedge, then basically it's really hard to escape that SI. Okay, so anyway, yeah, so that was a construction, and then again the conjecture is that so yeah, giving some LP values for these SI guys, so we'll give a good solution, but then it's impossible. Of course, it's impossible to partition V into like these SIs. So then my conjecture, I think it's a slightly more open. I'm just interested in whether like, it's going to be growing function of L or not. Okay, so I want to see whether like any integral partition will have this integrality gap of a super constant or not. Okay, so I think this is kind of nice looking problem. And then yeah, well, much more, 3 more, but then let me stop here. Thanks.
Any questions?
Yes.
I have 2. I'll start the first one. So you said you had at some point this conjecture about tree deletion,
yeah,
so vertex deletions to remove some tree. Do you know something about deleting towards excluding all subdivisions of a fixed tree?
Oh, no, I think parity, I haven't touched it yet.
Also,
So you fix a tree, and now you want to delete a small set of vertices such that your graph does not contain any subdivision of this fixed tree.
so that's same as minor.
It's same as topological minor.
Yeah.
So if you have large degree vertices, it's different.
In hindsight, I should consider this like the parity, given this like the stupid difference between like the star and double star. Yeah, I think it might be fun.
I have a second one.
Yeah.
You said something about deletion to H minor 3 when H is planar.
Yeah.
What if H is not planar?
So then let's go. Okay. Good. Thanks for asking the question. So I think so. Of course, yeah. So of course, like the most like immediate extension is like parameterization. I think there's a polynomial and approximation. But then I don't think even higher than that. I don't know anything. Yeah, there is no one.
Okay, so for this specific case we know, but
yeah, like K10, I don't know.
oh nice.
I don't think anybody knows. And then and then it's crazy that for any fixed minor, 2 approximation is still not ruled out. So any of these minor problems might be as easy as a vertex cover. That's how stupid complexity theory is.
So it seems that many of the algorithms you have are randomized.
Yes.
So so when you prove the hardness, do you also assume that it's hard also for randomized algorithm? Or?
Yeah, I mean, I don't think, I don't make a distinction. Actually, like, I think all algorithm that I mentioned, I just presented as a randomized algorithm, but if you want, actually, you can easily de-randomize it.
Oh, I see. So it doesn't matter.
Yeah, and then,
Will be the same approximation ratio or?
and then of course, like, eventually P is gonna be VPP, so I think, you can.
Any other questions? So if not, let's thank the speaker.